Temperature measurements are important in direct measurement and also in ancillary situations, such as determining the density of a gas. One way of measuring temperature is with a bimetallic strip. So this comprises two metals with different coefficients of thermal expansion. Whenever these are at a temperature other than that which they were bonded at, the differences in the elongations cause curvature in the strip. That curvature is given, the radius of that curvature is given in this expression. So you can see that as temperature increases, the radius gets smaller. So you have more deflection of the tip. And whenever the temperature is equal to the temperature at which it was initially bonded, then radius is infinite, so the strip is flat. And this strip is often used to control switches and thermostats, such as in a toaster. The other terms in that expression are the coefficients of thermal expansion and ratios for the two materials, so the thickness of one over the thickness of the other, and then the ratio of the elastic moduli. Thermocouples are possibly the most common temperature transducer, and they're based on the Seebeck effect, where electric potential is generated by a dissimilar metal junction whenever it's at a temperature above 0 degrees absolute. The strength of that electric potential depends on the junction temperature. There are a couple of things to consider whenever using thermocouples that might not be obvious at first. One is that there needs to be zero current flowing through the junction. As stated earlier, the Seebeck effect causes is when a temperature gradient causes a voltage potential, or a voltage. The dual of that effect is the Peltier effect, which is whenever a current flows through a junction, heat is either removed or added, depending on the direction of the current. So if there's some current flowing through our voltage gauge, then that will change the temperature at the junction. Another consideration is that whenever we're using a thermocouple, when we connect it to our voltmeter, we've added two more junctions of dissimilar metals. For example, if material 1 is iron and material 2 is platinum, then now we have an iron-copper junction and a platinum-copper junction. Thermocouples are typically used with a data table, and those tables provide voltage difference between a junction at 0 degrees C and at some sense temperatures. And that reference temperature is typically 0 degrees C. So if T1 is your sense temperature and T2 is 0 degrees C, then a data table will tell you what voltage to expect for those temperatures. And you can use, if you measure a voltage that's not in the table, you can use linear interpolation to determine the temperature here at T1. But it's not practical to maintain a 0 degrees C reference temperature, so we can use the law of intermediate temperatures. T2 in this example would be 22 degrees C, and so if we had T1 was 0 degrees C, T2 is 20 degrees C, or 22, and T3 was our sense temperature, then we can use the relationship that this voltage here is the sum of the two voltages, E1 and E2. Let me reorient this drawing just to show that differently. So here is an implementation of a thermocouple, and this wire is material A, and then these two wires are the same material, material B. So now we have a material B and copper junction here, and a material B and copper junction here. The voltages from those two junctions will cancel each other out as long as these junctions are at the same temperature. So now we need to find the difference between the voltages at 22 degrees C and at our sense temperature. So this is equivalent But the voltages that we have from our table would be the difference between 0 degrees C and our measured temperature. So here's where we use this law of intermediate temperatures. So we have T1 and T2 are 0 and 22, T2 and T3 are 22 and T, and then T1 and T3 would be the values given in the table. So 0 and our sense temperature. So we can use the table to find the voltage at 22 degrees C relative to 0. And then we also know the voltage at other temperatures, so we can use that for E3. So we get E1 from the table, we measure E2. So the voltage difference between 0 and 22 is 0.87 millivolts. The voltage that we measure is the difference between 22 and this sense temperature is 5 millivolts. And so that adds up to 5.873 millivolts. So if we had this junction at 0 degrees C and this junction at the same temperature that we're measuring, we would expect to get 5.873 millivolts, given that we know this one is at 22 degrees C. And so then we can refer to the table to see what temperature corresponds to 5.873 millivolts. And for one type of thermocouple, it would be 133 degrees C. This table shows the different voltages with respect to temperature for different types of thermocouples. And when the term thermocouple type is used, that refers to the two types of metal that are being joined. So these all have different characteristics. You can see that type E is shown here, and it has a range of up to about this value. So you can get other materials for different types of thermocouples that have a greater range, so they might be more expensive because the materials, the metals are more expensive. Or you could get cheaper materials. Different thermocouples have different sensitivity, so that is the relative change in voltage with respect to change in temperature. So there are different considerations when using different thermocouples, and some have chemical reactions to materials they come in contact with, whereas some metals are less reactive. So for the table, the voltage you measure, it's imperative to know what type of thermocouple you have in order to extrapolate the temperature that it's measuring. So for example, a type T thermocouple measures 4.3 millivolts at 100 degrees C, but a type E thermocouple would output 6.3 millivolts at the same temperature. Instead of linear interpolation, one could use a curve fit to get a better approximation for the intermediate values, and a third order curve fit is often adequate. And this is given in the textbook. Equation 812 yields the polynomial for curve fitting the data from a thermocouple table. In summary, we looked at bimetallic strips where the displacement is generated as a function of temperature. This is nonlinear, and it's often used either as an on or off switch, so just in a binary application. Thermocouples, on the other hand, output a voltage instead of displacement. They're nearly linear, and they have uncertainty of about 0.5 degree C. So it's not great accuracy or precision, but the temperature range is quite high for thermocouples. Here's one example, which is problem 812 in the textbook. We're given a chromel-alumel thermocouple, and the temperature at which the sensing junction is placed is 100 or 1560 degrees Fahrenheit, and the reference junction is at 83 degrees Fahrenheit. So the junction box where it's connected to the voltage sensor is 83 degrees Fahrenheit. And so we want to find the expected voltage reading. Since the table in our textbook is in degrees C, we'll start by converting these temperatures to Celsius. And then we'll use this relationship that the voltage we would get if the junction was at 0 degrees C and the sensing temperature or sensing junction was at 849 degrees C is equal to the sum of the voltages from 0 to 28 degrees and from 28 to 849 degrees. And we'll call these voltages E3, E1, and E2. So E2 is what we would measure. It's the difference, or it's the voltage difference between the 29 degree junction or 28 degree junction and the 849 degree junction. So E2 is equal to E3 minus E1. E3 we can get from the table. So E3 would be the voltage from 0 to 849 degrees. And linear interpolation gives us that E3 is 35.231 millivolts. And this is for a type K thermocouple. And E1 is also available from the table. So the voltages between or bracketing 28 degrees Celsius are 1 and 2.023 millivolts. So linear interpolation gives us that E1 is 1.14 millivolts. So we find out that we would expect to measure 34.095 millivolts in this case.